All right, so let's move into average rate of change. So average rate of change is what we want to think of as slope of the secant line. Remember I had you finding the slope of the secant line? The secant line was a line drawn between two different points. So average rate of change is between two different points, A and B, and it finds the change in the y values divided by the change in the x values. So it is slope of the secant line. And that's the same as saying average velocity, change in distance over change in time. Like f is given to give you the function where the position of where an object is, change in distance over change in time. So both of these things mean the same thing. So we can use f of b and f of a. So let me just give a little picture here, a and b. So the functions here to here, this would be f of b, this would be f of a. So change in the y values, f of b minus f of a, all over b minus a, which would be the change in the x values, right? So that's a representation of this, and that's what we've seen before is the slope of the secant line. Okay, so that same thing can be represented in this picture. So let me just draw it here. So if I have a and a plus h, so just a little bit of different notation. So this would be f of a, and this would be f of a plus h. So then my secant line would be here. So my change in distance, f of a plus h, minus f of a, over the change in time, well, this distance would be h. So that's what this is. So they're representing the same thing, just a little bit of different notation. So this is, both of these are using the function f of x, f of x. Here, we're using s. And lots of times we use s of t because we're talking about a position with given time t. Again, this is just the difference h. So just a little bit of notation, not necessary to get overwhelmed. These all meaning the same thing. All right. So got some pictures here. So if I have the red function x cubed, so the blue secant line is between 2 points, 0 and 1. And so we can see the slope of that blue secant line. The green secant line is between the points 0.5 and 1. The purple secant line is between the point 0.9999 and 1. So what I'm doing is I'm taking secant lines that are between 2 points closer and closer to each other, where these 2 points are really close to each other. And so what we're going to do is have these secant lines get close and close to be close to a tangent line. So if I take the secant line between the point 1 and 2, that's the blue one, or between 1 and 1.5, that's the black one, or between 1 and 1.0001, again, the purple secant line is between 2 points that are really close to each other. Just like the purple secant line here is between 2 points that are really close to each other. To get really close, I think that you know we've been doing that. That looks like it's been our limit. So this purple secant line from this direction by finding points close to on this side, or the purple secant line coming from this direction from finding 2 points close on this side. Now that really seems like a limit. We're coming from both sides. All right, so let's develop this further. What we're going to be doing is we will be taking a limit. And notice there's no plus minus, so we are doing it from both sides. So when I take the limit, f of x minus f of a, so here would be a, here would be x, and I let x go towards a, the 2 points, I'm letting this point get closer and closer, so then I'll be finding the slope of the tangent line at that point right here. So that's what this does. So this gives you, with the limit, the slope of the secant line turns into the slope of the tangent line. And then same idea here on this one. If I have a and a plus h, And again, my 2 points, f of a and f of a plus h. If I let h go to 0, that will move this point to this point becoming closer and closer to here. So I'll find the slope of that tangent line. So the slope of the tangent line is called the derivative. And whether we're using the definition with h going to 0, or using the definition without h with x going to a. So I have two different definitions, and I have the application of it calling velocity if I change the function name to s, and I use t's instead of x's. So all of these things mean the same thing. The derivative, the slope of the tangent line, instantaneous velocity. All right, so keeping in mind these two definitions, this one here, the definition without h, this one here, the definition with h. So this is kind of like a Jeopardy question here. So looking at this definition, so this is kind of like Jeopardy. Here's the answer. What was the question? What was the f of x and what was the a that I was using to make the derivative? Well, looks like I'm using the definition with h, since I have an h here, h going to 0, right? So let's look at this. Should be a plus h. So I think a is going to be 3. So this would be a plus h, subtract 3, I think it's going to be x squared. So this would be f of a plus h, 3 plus h squared, minus 3 squared all over h. So if this was the function and the value of a, this would be the definition of the derivative. All right, let's look at this next one. This looks like the definition without h. So the definition without h, let's look at it again. So x minus a on the denominator, f of x minus f of a on the numerator. All right, so because it's explicitly said, I think a is going to be 2. And this is f of x, and this is f of a. So f of x has got to be x cubed. All right, next one. This looks like the definition with h. So this has to be f of a plus h. So I think a has to be pi over 2. This has to be f of a. So I think the function has to be sine of x, and sine of pi over 2 is 1. So limit with h, the h's are going to 0. Without h, so this is the limit without h, this is x minus a. So a has to be pi, and this has to be f of x minus f of a, minus f of a. Cosine of pi I know is -1, so that would be a -1. So I think cosine is the function.